you have a T, and A is really the subset of a V. I would have used U if it is a subspace. And I think you have learned probably this notation, and TA, in the proof course, right? Do you know what the TA is? A is a subset of a vector space V. Then this is a collection of all the vectors that is coming from A, right? And you stick it into a function T, linear map, and see what you get. The collection of all of those, right? Sometimes there's an overlap, right? Because it's not injective, but the collection of those. So this is a new notation. From that notation, do you agree that range of T is T of what? If T is coming from this endomorphism V. Range of T, according to that notation, range of T is exactly T of V. Is that right? You send everything under T, and then what you're going to get is exactly the definition of range of T. Right? So we already have that notation, but it's convenient for subspaces, right? Right, so how about this one? What if I write T of V prime, where, what is the V prime? Do you know the V prime? V prime was typically rises like this, null space of T and any complementary part, right? Right, null space under T doesn't do anything. If you get something non-trivial here, that is the contribution from V prime. Okay, so from there, you get also the same result in knowing that T is injection on that part. Is this notation okay? T of a subset is a subset. T of a subspace is a subspace. All right? All right? Okay. So under that, invariant property is described very nicely. Invariant under T. How would you write it? U is invariant under T if T of U, what should happen? If I send everything on T, where should it go? Back inside U, right? So it has to be inside U here like this. Isn't that nice? That's a notation. If U doesn't escape under T, go back to inside U, that's exactly what I mean by invariant, right? Okay. Any question? Right. How about the next idea is indecomposable. So let's think about decomposable, easier to write down. So decomposable subspaces. Means if I have a U, then I can write it down to W1 plus W2. Right? If it is not one-dimensional, probably you can do that. If it's one-dimensional, there's nowhere to go. So when is this decomposable subspaces? If W and W2 are what? This is decomposable under T. That's the thing that I'm emphasizing here. We're saying that W1 should be invariant under T and W2 should be invariant. That's the idea. So W and W2 are invariant. You can always write down the direct sum no matter what, but there's additional condition when we talk about this decomposable under T. It's this invariant under T. Right? So if you split it like this, W2 doesn't escape, W1 doesn't escape, it has to go back inside of W1. W2, and you hit it with a T, should go back inside W2. That's the idea. All right? And why we're considering this? If the map is complicated, it looks like this all juggled up in here according to the standard, for example, standard basis, then there is a different way of looking at it, isolated. This subspace is not mingled up with the W2 under T. This is all happening inside W1. W2 invariant, all happening inside W1. So although it's a gigantic map, it's actually two separate maps. They never interact each other, so that they decompose into a simpler and simpler map. That's the idea. So if this is indecomposable subspaces, this cannot happen, right? There is no two invariant subspaces. You can write it as a direct sum. If that cannot happen, we say it's indecomposable subspaces. Make sense? And then from there, not possible, then it's indecomposable under T. All right? So that's where we stop. We start with a gigantic map, and you go keep splitting until you cannot do that anymore, and that's indecomposable subspace. That's our goal here. So I need to actually be careful in this order. All right, so with that notation, also I introduced this EA. But remember EA? It's not a video game. It's a V inside V there, and TV is A times V. Is that right? Lambda. All right. So it's a slightly different notation. How about TV minus AV? Is that okay? And they also write like this: TV minus A times IV. I is not the matrix. I is the identity map on V, right? V is abstract vector space, so there's no matrix. It's just identity map. And V here, even not nowhere it requires in this all things here we're considering, there's no finite dimensionality required in here. Right? So that, and you read about this polynomial applied to operator thing, right? That's so here, this is a map as a linear combination, so we can pull out like this. This is notation. This from here to here is the meaning of this notation. Right? T minus AI as a linear map, what it does to a vector is this. Okay? And then if V's came from here, we're looking at all these things being 0. Is that right? 0. You've seen this thing before. T minus AI. What do? Have you seen that before in terms of matrix, right? M minus lambda times the identity matrix. You use that to compute determinant and the eigenvectors. But here, without determinant, because there's no matrix in here, and this is a description of a null space, something went to 0, isn't it? So therefore, we have a new description of EA. Null space of what kind of map? T minus AI. It's new space. Anything under here going to 0 means it's actually eigenvector of eigenvalue A. All right? That's nice. Nice description as in terms of something you already know. It seems like eigenvector is some complicated notion, but it was simply just null space of this very interesting map. It is like a linear polynomial, right? T minus A times 1, kind of, right? It's a linear polynomial. That's the idea. So this operator became very, very important into splitting the space into indecomposable spaces. Turns out it's the right idea to apply and strip off complicated matrix into a simpler shape. Thing is, everything we know is just described in slightly different terms and notation-wise and things like that, right? All right. So next thing is this little bit of example. Think about it a little bit more. I think one more time, so see if that's what I want to do. Exactly, that's what I want to do. So here let's say the dimension of EA is 3. All right. So what does that mean? We're looking at some vector space, and we calculated all the eigenvectors, right? So how many eigenvectors are there? Trick question. Infinitely many, right? How many independent eigenvectors of eigenvalue are there? 3 of them. That's what this means, right? There are infinitely many eigenvectors for eigenvalue A, but 3 of them only linearly independent. All right. So here's a question. Can we say something about this indecomposable property of this EA? EA has a dimension 3, right? Obviously, it's going to split to E1, U1, and U2, and U3. Is that right? It has a dimension 3. So U1 has what is the dimension of each of the U1? UK. It has a dimension 3. Direct sum must be dimension 1, right? Okay. So this is a direct sum, but is this indecomposable? decomposition. That's the question we have to ask. It's about how it behaves under T, right? So let's say, is this a question? If I send everything along U1, is this going to be in U1 again? Let's say it's UK. That's the question you have to. It's invariant, right? If so, then this is going to be what? Right, it's decomposition, indecomposable decomposition. Is that right? So do you believe it's true? Or is just nothing is given? How can you conclude something like that? What was your reaction? This is very special. All this thing has this property that T of V is what? Because it came from eigenspace, therefore it's A of V, right? So what happens if you multiply the scalar to U1? It stays inside V1, right? It's a scalar multiple, right? So if V1, V is in UK, would you believe that A times V is in UK as well? The very property of a subspace. So T of UK, everything inside UK is going to go back inside UK, correct? Therefore, this is indecomposable decomposition. Right? This is the invariant decomposition. And these individual are, because you dimension 1, can't go any further, right? Yeah. So, if you have enough number of eigenvectors, then the indecomposable, the decomposition into invariant spaces is just all one-dimensional, I think. So let me state that, the theorem. So observation. Its dimension of a V is n, and if we have n linearly independent eigenvectors of multiple eigenvalues, not just eigenvalue of A, we have three-dimensional eigenvalue space A is something different. B, that also has eigenspace, right? If they're all of them, and they're going to form a direct sum, which is a little bit missing logically, but I stated that last time. EA plus EB is direct sum. Remember that part? If A and B are different, they don't have intersection. Eigenspaces never have an intersection. So if I have n eigenvalues, some of them has a common this eigenvalue, and some of them has different eigenvalue. But if the eigenvalue is different, they're all direct sum. Because of that, V is going to split into EA1 first, one eigenspace, and EA2, different eigen. Let me just write out straight. This is more complicated. Here's a U1, U2, all the way up to UN. I have this n eigenvectors, right? And not all the same eigenvalue. For this one, we have lambda 1 eigenvalue. For that one, with lambda 2 eigenvalue, potentially they're different. That's what I mean by n linearly independent eigenvectors of all different eigenvalues. And this is all indecomposable invariant spaces, right? So UK's dimension is 1. Is that right? It has a dimension 1. We have n linearly independent vectors, so this is a direct sum. So that's what this one's about. And UK are invariant. Can you explain why this UK is invariant? UK's are all generated by one-dimensional eigenvectors, right? So because T of VK, let's say that was generated by VK, one vector, right, is VK times some scalar. Each of them has its own eigenvalues. Some of them could be the same. Therefore, it's back in UK, right? Scalar multiple doesn't change the space, so it stays in size. So UK's are invariant, and dimension 1 is indecomposable, right? You can't go any further. So this is indecomposable decomposition into invariant spaces, right? If that happens. So that was an exercise I wanted to go through to review this notation, some of the notations there I began to use. So let me just circle that part. It's an important thing that I wanted to cover. I'm not sure if I have time to cover that. Second example is this one. It's an important example that you did that in the quiz, I think. 2, 0, 0, 0, 2, 1, 0, 0, 2. All right? So if it is like this, it just looks a lot like that test problem that I just returned. And if you do the same thing, the only eigenvalue, this lower triangle here is 0, right? So if you subtract lambda and do that, it's lambda minus 2 cubed. That's the only thing you get. Only eigenvalue we have is lambda equals 2. There's none other. E2 is the only one. Then if you plug in lambda equals 2, that turns to 0, and then you solve the homogeneous equation, right? So you see that. So this is m to m. M minus 2 times identity matrix is what we're calculating, right? So what is the matrix here? If you subtract 2, that's a 0, 0, 0, 0, 0, 0, 0, 0, 1 there, right? Okay, so you can see these and these are the two free variables, right? So here, from there, we know the dimension of this eigenspace. What is the dimension of eigenspace? How many vectors are there that makes this one 0, which is the eigenvector, right? Null space of this one. How many free variables here? 2, right? There's a 2. All right, it's a dimension 3, right? It's a dimension 3, and there are only 2 linearly independent eigenvectors. So it's not going to be decomposed into one space and one dimensional space and one dimensional space like that. All right? But it has these 2 eigenvectors, and 2 eigenvectors turns out to be 1, 0, 0 with eigenvalue 2. If you calculate it here, 1, 0, 0 you calculate easily. What is the second one? I think it's a 0, 1, 0. That's exactly this correspondence here. So those are the 2 eigenspaces, 2 vectors in eigenspace. The question is that it's about the decomposition. The question is that is this R3 can be decomposed into E2, right? And direct sum of some other spaces. And we hope that this one itself is invariant, right? Because the eigenspace goes down to everything is a scalar multiple. It doesn't go out. That's another property. Is that okay? How about B prime? You're putting this one, if this is invariant going back to V prime, and what is the dimension of V prime here? It's 1. If it is a 2 dimension, and that has no choice, 1 dimension, right? So it's 1 dimension. So T, let me write a span of V prime is generated by, I'm going to say is V1 is generated by B prime. 1 dimensional, right? So what can happen to V W of V1, T of V1? You have to go back into this space, right? All the spaces here are generated by 1 element. So this must be scalar multiple of V1. Is that right? Whatever the scalar multiple is. Is that right? If this is the invariant, then this must happen. And what is this A called? Eigenvalue? V1 is A times V1 is eigenvalue. Right? It's a kind of direct sum. So A better not be 2. If so, it would have been inside E2, right? So this forces existence of eigenvalue that is different too, right? Correct? Yeah. So turns out you can't do this. If this is invariant, there's a contradiction. So you cannot decompose it E2 and something. That doesn't mean it's indecomposable. It's actually decomposable. So here's what happened. It seems like you can use this one vector. It's not easy to discover this one. So R2, R3 is a span of E1. It's an eigenspace. E1 here is an eigenvector, right? That's E1. So that's nice invariant space. And if you look at what happened between this vector and the third vector, you realize that you better not split this one. So first consider this one. Right? So where is this E2 going? It's an eigenvector, so it's going to multiple of E2. But what about E3? Where does E3 go under T? It's a 0, 0, 1, 0, 0, 1. So can you do that? 0, 0, 1. 0, 0, 0, 1, and 0, 0, 1, and 0, 0, 2. Is that right? That picks up the third column. Is that still inside this guy here, space span of E2, E3? It is true that involves only second coordinate and the third coordinate that is inside E2, E3, right? So this is the decomposition. So that goes to span of E1, and that goes to back to span of E2, E3. So this is invariant decomposition, correct? Each other component is mapped in there. That's good. All you have to do is splitting this one further. Correct? All right. So if it is not possible, then you conclude this is indecomposable. Right? And this is the really indecomposable factorization. So let's think about why this one is indecomposable. If it is decomposable, what is the possibility? Suppose decomposable. Then span of E2, E3 is going to split to, I'm going to use W1 and W2. Is that right? And it's not just a direct sum. What other property we're putting in there when you consider this indecomposable and decomposable thing? Invariant subspaces, right? So this has dimension what? This is dimension 2, and it has to be dimension 1 each of the time, right? So this has to go back to W1. This has to go back to W2. We looked at it earlier. If it's a one-dimensional situation, when you go back into inside, you have not much of the choices. So here's a W1 is generated by one vector, little w1. W2 is generated by little w2, right? Correct? So what's going to happen in here is that T of little w1 have to go back inside the span of w1. Therefore, there must be some sort of scalar like this, right? And T of w2 is going to be back in here, right? Invariant space. You have no choice. One-dimensional space. It forces another scalar to there. And what was the conclusion from here? By looking at this B1 and B2. Hey, those B1 and B2 are eigenvalues? Eigenvalues again. This is eigenvalues. So we discovered one eigenvector and another eigenvector linearly independent from that, and there was one eigenvector, right? So how many eigenvectors did I find? E1 and this fictional 2 more. So I found 3 linearly independent eigenvectors, right? But I calculated it at the very beginning, right? There's no eigenvector. The only eigenvalue is 2, and the dimension of that eigenspace is 2, not 3. Okay, so going down, What's the conclusion in here? We suppose this thing then it violates the dimension of the eigenspace. Therefore, it's not decomposable. You see, this heavily relies on the one-dimensionality when you split it. So if this gets a little bit longer, it is fairly difficult to determine why this one is indecomposable. For example, the third example. So do you think it concludes that our discussion? This is the split is invariant subspace and invariant subspace. One dimension, you can't go any further. And this here, I argue that if it is splits into invariant spaces, it violates the size of the eigenspaces. Therefore, we can't decompose any further. Therefore, this is indecomposable. And this is a final state. You can't split it any further into invariant spaces. So this is a final decomposition. And it came from this matrix, upper triangle matrix. So this kind of, they put it like this, and you can see this block matrix and a block matrix is completely isolated, and that's where it's coming from. So if you make it all together like this, 2 and 2 and 2, and 1 above and 1 above, doesn't matter if it's 0 there, it's the simplest form. If you do like this one has the lambda equals 2 is the only eigenvalue, and dimension of E2 this time is just 1. And this one is indecomposable. You can't, the whole R3 is indecomposable. You can't split it any further. And to do that, it gets a little trickier. And it is not, the proof doesn't go to, from here I'm going to introduce a slightly more general method to understand why this one is the smallest map that you want to consider. So again, we started with a large map, and we want to get down to this much of a small spaces, invariant subspaces. All right, so I'll stop here.